Hello and welcome everyone to this month's SNOMED CT research webinar. I'm Susie Roy, the Customer Relations Manager for the Americas and Research Engagement Lead at SNOMED International. And as always, the host of the SNOMED CT research webinars. We're all very accustomed to Zoom webinars at this point, but just to provide the customary openings here, you'll notice that everyone is currently muted. But of course, if you have any questions as we go along today, please enter your questions into the Q&A box. And at the end of today's presentation, we'll have a dialogue, a Q&A portion where Professor Fernandez and Francisco will answer all of your questions. This webinar is being recorded. Both the video and the slides will be made available later this week. So for those of you who are new today, of course, welcome. Just to let you know that in addition to our research webinar, we also have two other tracks. We have a clinical track and an implementation track. These other webinars focus a little bit more on the actual clinical implementation of SNOMED CT, whereas this research webinar is all about research on and with SNOMED CT. All of our webinars are always free of charge. You just have to register in order to attend live, or you can watch the recordings later. And you can visit snomed.org/webseries to see upcoming presentation for each of these tracks. And if you've missed any of our webinars, the clinical implementation or research webinars over the past 2 years, you can go to our SNOMED International YouTube channel. And you can see all of these videos as well as many other videos. And I suggest that you like and subscribe so you are notified when we post new SNOMED CT videos. If you would like to be notified of upcoming research-related news and events for SNOMED CT, you can join our SNOMED CT research reference group. This is just a Google group where I pretty much push information about upcoming research news. To join, you just need to email me at sro@snomed.org, and I will get you on that list. And just to reassure you, there are only like 3, sometimes 4 emails that I push out each month. So it's not going to overfill your inbox, I promise you. And one last little plug that I wanted to announce for today is that registration is open for our upcoming annual October SNOMED CT Expo. Oh, that was a nice transition. Last year, we had almost 2,000 people from over 60 different countries attend our virtual event. And we had even more views of the presentation online even after the event. Registration is open and it's free to attend, so we really hope to see you there. If you have any questions about the expo itself, please don't hesitate to contact me. Again, my email is sro@snomed.org, and I would be happy to answer any questions that you have about that. Okay, and now for the main event. So Professor Jesualdo Tomás Fernández Breis is PhD in computer science and head of informatics and computer systems department and director of the Masters in Science and Bioinformatics at the University of Murcia, Spain. He's a member of the IMIB Breis Biohealth Research Institute. His current medical informatics research lines are the application of semantic technologies for the development of learning health systems and the development of ontology quality assurance methods. Francisco Abad-Navarro, PhD candidate in computer science at the University of Murcia, Spain, sorry about that. Since 2016, he has been a research assistant with the Department of Computing and Systems in the university. He is a member of IMIB Breis Biohealth Research Institute. His research interest focuses on semantic web technologies and its applications such as ontology evaluation or information retrieval and bioinformatics. Professor Fernandez and Francisco will be presenting today the analysis of readability and structural accuracy in SNOMED CT. And with that, I will stop sharing and let you guys take the screen.
Okay, thank you, Susie, for the introduction. Hello, everyone. I'm Jesualdo. I'll be happy to share this presentation with my PhD student, Francisco. And first, we would like to thank SNOMED International for inviting us to share these results with this community. And in order to reduce the bandwidth needs for the audience, I'm going to switch the video off during the presentation. I will turn it on back at the end of the presentation. So first, I will introduce a little bit the agenda of the talk. I will talk a little bit about us, our research group. I will provide some background and motivation for this work. And then Francisco will do the hard work of this talk. He will introduce the metric we have defined for readability, for structural accuracy, and how we have applied them to SNOMED CT. I will present some conclusions at the end of the talk. For those who are not familiar with Spanish geography, we come from Murcia, which is a sunny region which is located in the southeast of Spain. We have the largest salty lagoon in Europe, which is some days experiencing some problems. You may have heard or read in the newspaper about this. And Murcia has also a history of contributions to engineering. We have some very important inventors like Isaac Peral and Juan de la Cierva, who invented the submarine and the autogyro in the 19th and 20th century. Unfortunately, we haven't invented so nice things. The researchers were presenting this work today, but we belong to the Technomod research group, which we have been doing research on ontologies, knowledge technologies, and language technologies for the last 20 years, more or less now. I think we started in 1999, more or less. And we are based mainly in the Faculty of Computer Science at the University of Murcia. Most of the members of our group, we have a computer science background, although we have some members who have studied biotechnology, biology, or biochemistry. We are also members of the Murcia Biohealth Research Institute, which allows us to collaborate with clinicians and other types of biomedical researchers and to develop more applied research lines. Today, we will be presenting the results of the article entitled Analysis of Readability and Structural Accuracy in SNOMED CT, which was published last year in a special issue on quality assurance in BMC, medical informatics and decision making. You can see that this paper has 4 authors, it's Francisco and myself, but also Manuel Quesada and Astrid Duque participated in this work. And as you will see in this presentation, their work was important in order to achieve these results. For those who are not familiar with ontologies, we could use the traditional definition, which says that an ontology is a formal, explicit specification of a shared conceptualization. And basically, this means that it is a conceptualization. This is a model in which we include the concepts, the relation that hold in a particular domain. Formal means that this is expressed in a way that machines are able to process this, the content of the ontology. And shared means that this conceptualization, that this model has been agreed by a community, by a group of users. One of the features of ontologies, which is of paramount importance for our work, and you will see this in this presentation, is that the content of the ontologies should be understandable by both humans and machines. So the content of ontologies should be human-friendly and also machine-friendly. If we think about the role ontologies have been assigned in the last decades in the field of medical informatics, we will probably agree that the most relevant one is to be a technology, or to be the technology that should enable the achievement of semantic interoperability in the healthcare domain. And that will only be possible when different systems involved in this area of medical informatics or healthcare share the conceptual model. And this means that this will only happen when EHR systems exchange the data of the patients, sharing the meaning, sharing the concept, sharing the conceptual model, when EHR system and clinical decision support system do the same thing. They share the conceptual model, they share the ontology, and this can be applied to any type of system that should interoperate in this domain. This is not a novel idea. This has been the idea of the community for the last 20 years. These days we're celebrating 20 years of this paper published by Alan Rector and colleagues in the Artificial Conference in Medicine in Europe. And actually this was a very important conference for me because this was my first medical informatics conference, and we are still talking and doing references to the work presented there. And in this paper entitled Interface of Inference Models with Concept and Medical Record Models, Professor Rector and colleagues proposed the existence of 3 different types of models: patient, the data model, the concept model, the ontologies, the inference model, which are the guidelines, which need to communicate, which need to interoperate in order to obtain the semantic interoperability. And actually, one of the conclusions I drew from this paper, from this talk in the conference, is that ontologies should be the bridge between the data and the guidelines. More recently, you may have heard of this network of excellence called Semantic HealthNet, which ran from 2011 to 2015 or 16, more or less. They identified 4 major axes of action that need to be developed and that need to cooperate in order to achieve the semantic interoperability. 3 of these axes correspond more or less to the types of models proposed by Rector and colleagues. We've got the information, it's related to the data and to the EHR. We've got the concept related to the classification systems, terminologies, ontologies, and we've got the inference related to the guidelines and related to pathways and to the decision support. In one of the deliverables of Semantic HealthNet, we can read this sentence, these 2 sentences: clinical models must be designed by sharing the same clinical process and concept models. Sharing the same concept model means that clinical models and clinical guidelines share the same ontology for representing their concepts. So again, ontologies play a central role for the communication, for the exchange between the data and the guidelines. Plays a fundamental role for the achievement of interoperability. And the importance of ontologies is so big in this context that Semantic HealthNet in the roadmap identify the need for the quality assurance of all these semantic resources, all these ontologies, which were meant to be consumed by the machines, by the application that would exchange the data, assuming that the content of this ontology, which are providing the meaning to the data, are correct. So there's a need for ensuring that these ontologies, these terminologies, these semantic resources in general have a certain degree of quality. If we try, let's have a look now to how SNOMED CT represents the knowledge, and we can illustrate this knowledge representation in SNOMED CT using an example that has been extracted from the SNOMED CT browser. We've got the concept congenital stenosis of aorta. We can see that in order to describe the congenital stenosis of aorta, we use some terms, some labels, which are content in natural language, which can be understood in an easy way by humans. We've got hierarchical relations, we've got ancestors, we've got children, we've got codes, which are unique identifiers for the concepts in SNOMED CT, and this is very good for machine processing. And we've got properties. These properties permit to define relation between concepts. For example, congenital stenosis of aorta is linked to aortic structure and linked to congenital. And the machines are able to identify the relation between congenital stenosis of aorta and aortic structure, and between congenital stenosis of aorta and congenital are different because these properties have a particular meaning, have a particular name, have particular properties. So making this information about the properties machine processable. So at the end of the day, in order to represent knowledge in SNOMED CT, we've got the terms, we've got the codes, we've got the hierarchy, we've got the properties, and altogether contribute to delineate and to define or describe the meaning of every concept in SNOMED CT. And we think that all these elements should be taken into account when developing ontology quality assurance methods. If we try to provide a definition for ontology quality assurance, we can say something like, is the set of activities that ensures that ontologies meet their design requirements or expected use. And in the field of engineering, when we talk about quality, it's very usual to relate to the quality with the degree of accomplishment of a certain set of requirements. And we are aware of the fact that organizations which are developing and maintaining large resources such as SNOMED CT or the gene ontology in biology have developed their own quality assurance processes. But such resources are so large that it's very difficult to handle and to control every single aspect of quality in these resources. And this is more difficult in a field like ontology quality assurance, which lacks of standardized methods, frameworks, and tools, despite there are a number of people involved in this area. A few years ago, we did a study on the content of the bioportal repository, which is probably the most important repository of biomedical ontologies, and we drawn some conclusions from the quality assurance perspective. On the one hand, there is a best practice in ontology design, which is to reuse content from other ontologies, because if we are reusing consolidated knowledge, this will mean that our ontology will be of a higher quality. But we found that there was low effective reuse of content from other ontologies, but due to some properties of the content of the ontologies, there was a high potential for reuse. So there was room of improvement, and there was a space there for developing ontology quality assurance methods tackling this or addressing this aspect of this limitation of the ontologies. We also found that many of the ontologies were nearly plain taxonomies and were using few types of axioms. This means that the content processable by machine was limited, was not as much as possible. On the other hand, the content for humans was quite rich because these ontologies were rich in natural language. And we found that many of these ontologies applied naming convention. And a naming convention, the application of a naming convention means that if we have concepts which are close in the hierarchy, in the taxonomy, the labels of these concepts are quite similar, which is good in order to develop methods for quality assurance. Given this picture and this situation that we found in this repository, in our research group, we defined or we wrote some research questions related to ontology quality assurance. And in this presentation, we're going to talk about two of them. The first one is, can we use quantitative metrics to objectively analyze quality aspects of ontologies? And the second one is, can we detect errors in ontologies by exploiting its content and structure? Our proposal for answering the first question was the OQuaRE framework for the evaluation of ontology, and this was the topic of Astrid Duque, PhD. So basically, we defined a framework for evaluating the quality of ontologies, and this required to define a quality model which included a series of quality characteristics. For example, we want to evaluate the quality of the structure of the ontology. That would be a characteristic. This characteristic is evaluated through a series of sub-characteristics, in this case, for example, tangledness and formal relation support. These sub-characteristics are evaluated through a series of quantitative metrics. So at the end of the day, we're able to get some scores for these metrics, which are used to generate some scores for the sub-characteristics, which are used in order to get some scores for the characteristic and given to the whole ontology. However, what is more important than getting these scores is that the metrics are able to inform about flows and strengths of the ontology. And this is what is really relevant from the point of view of quality assurance. We defined 19 metrics which were related and capturing different aspects of the quality of ontologies, which are like the ones listed in this slide. But I'm not going to explain them, because what I want to remark, what is important, is that the results of the experiment that we performed were that metrics allow for evaluating the quality of the ontologies. Maybe we were not, there are not metrics to evaluate all single aspects of quality of the ontologies, but we can use them in order to measure, to evaluate the quality of the ontologies. Metrics contribute to the analysis of the evolution of the ontologies, because changes in the values of the metrics can inform about changes in the modeling of the ontologies. And the values of the metrics are also useful in order to distinguish the content between different repositories. So they can be used in order to profile the content of the repositories. And when we did these experiments and we look back at our OQuaRE framework, we realized that despite we had, I have just talked about the richness of existing ontologies in terms of natural language, we didn't have any metric in the OQuaRE framework which was really exploiting the natural language content of the ontology, which is one of the richness of this ontology. And this was one of the reasons to start thinking about creating metrics which exploited the content, this natural language content, such as readability and structural accuracy, which will be presented by Francisco in a few minutes. In order to answer the second question, the detection of errors, we developed this OntoEnrich framework, which was the topic of Manuel Quesada's PhD. The hypothesis here was that the natural language content of the ontology should help to detect and to identify potential errors in the ontologies, to detect flaws or potential flaws in the ontology, which is important from the quality assurance perspective. And at this point, we could think if SNOMED CT contains modeling errors. And let's consider this situation in which we have two concepts, congenital stenosis of aorta, and on the left-hand side, and congenital stenosis of aortic arc on the right-hand side. Both concepts are children of congenital stenosis. If we look at their properties, we would see that, as expected, both occurrences are congenital, which is an expected result. Both finding sites are different, but they make sense because the aortic structure is related with congenital stenosis of aorta, and aortic arc structure is related with congenital stenosis of aortic arc. However, if we look at the third one, we would have probably expected that both concepts were linked to congenital stenosis, but this one is linked to stenosis. If we look at the label of the concepts, both are congenital stenosis. So we could think, or we could propose, that this link is potentially wrong, and that this link should be made to, or this associated morphology should be linked to congenital stenosis. And the goal of the OntoEnrich framework, the goal of the method that we developed at this time, was to be able to identify such situations which could suggest potential errors, because the fact that we are suggesting this do not necessarily mean that this is a modeling error, because that's the responsibility of the content editor to revise the decision. But it is the responsibility of a quality assurance method to inform about the potential flaws that can be identified in the resources. And actually, if I'm not wrong, this was an error which was reported in SNOMED CT and which was fixed by the SNOMED CT community in a later version of SNOMED CT. In our work, we have been inspired by the Lexically Suggest logically defined principle, which was proposed, again, Professor Rector and Luigi Giannone a few years ago. And we interpret this principle as follows. What can be expressed in natural language for the humans should be expressed as logical actions for the machine. So again, the content for the humans should be equivalent to the content for the machines. And we perform a study by applying this method that we developed in order to identify potentially missing relations to a module of SNOMED CT. And we found a high number of situations similar to the one of congenital stenosis. This doesn't mean that there are so many errors in SNOMED CT, but this means that we found situations that deserve to be revised, and the content editor, the domain expert, to make the corresponding decision, because there are some warnings from the quality assurance perspective. When we did this work, we started thinking in the research group, and we asked ourselves whether these potential errors could be associated with some kind of quality property of the ontology. And this is why we came up with this idea of creating this metric for structural accuracy, which will be presented by Francisco again in a few minutes. And this is where my part of the presentation finishes. I pass the baton to Francisco. So I'll stop sharing screen. So Francisco.
Okay, I'm going. So here we are, I think. So thanks for the button, Jesualdo. And well, my name is Francisco Abad from the University of Murcia, and I'm going to talk about different metrics closely related with the human readable content of ontologies. So the first set of metrics covers the readability, which is the capacity of an ontology to be understood by humans. So the second set of metrics are related with the structural accuracy of ontologies, but focusing on the human readable content by checking if it's in line with the semantic definitions or not. So let's start with the readability. As I said, the readability measures the human readable content in the ontology, such as names, synonyms, or descriptions. In this way, a high readable ontology implies that its elements are enriched with this kind of content. And this provides several advantages. So for example, it improves the understanding by humans. So here you have an example where a single concept has many synonyms, and the clinicians use a different set of synonyms depending on their background. This could provoke misunderstandings between different departments. However, a high readable ontology would link all the synonyms to the same concept, and ideally, it would include a human readable definition so that any human can understand the concept without any ambiguity. But high readability is not good only for humans, but also for computer agents, because it makes it easier to perform natural language processing tasks. For instance, an identity recognition system can be built by using an ontology as a dictionary, and the precision and the recall would improve if the underlying ontology has a high number of synonyms per concept. For instance, here we have two similar clinical nodes in which an identity recognition task was performed. The one on the left contains 3 concepts successfully identified, whereas the one on the right includes a synonym of absence of bone in arm that are not present in the ontology, thus preventing its recognition. So as we can see, the readability is an important aspect of ontologies, and for this we developed a set of quantitative metrics aimed at measuring the readability of ontologies. These metrics count the number of names, synonyms, and descriptions per concept and per role, if we speak in the SNOMED terminology. And I think role is also known as relationship. So we work with the old version of this SNOMED CT. So here you can see the translation between both models. The fully specified name is translated into a label, whereas the preferred synonym is converted into a preferred label, being considered both as names. Acceptable synonyms are translated into alternative labels, and these are considered as synonyms. And finally, the definitions are translated into the definitions under this discussed namespace, and they are considered as descriptions. Besides, a SNOMED CT concept is a class in the old representation, whereas a SNOMED role is an object property. So as these metrics were developed focusing on owl ontologies, hereinafter, I will use this owl terminology of classes and object properties. So here you can see an excerpt of this SNOMED ontology that demonstrates how the metrics are calculated. Imagine that this is our complete ontology, which consists of 5 classes marked in the blue circles. In total, these classes are linked to 5 preferred labels, which are considered names. Therefore, the ontology has a global value of 5 names over 5 classes, which makes 1 name per class. In the same way, the classes have 2 alternative labels, which are considered as synonyms. And in this case, the ontology has a global value of 2 synonyms over 5 classes, resulting in 0.4 synonyms per class. Finally, there are not any descriptions, so the ontology would have 0 descriptions per class. And this is also applies for the object properties, associated morphology, and finding site, which are also codes with names, synonyms, and description in the ontology. However, this is not taken into account in the figure for readability reasons. Besides, each entity in the ontology has its own individual score. So for example, the concept marked in the figure has 1 name, 1 synonym, and 0 description. This individual score is useful for detecting outliers entities with very high or very low values. So we apply this metric to the SNOMED CT, and what we found is that the ontology has more than 350,000 classes, and these classes have 2.07 names on average. Most of them have 2 names corresponding to the full specified name and the preferred synonym, which was considered as a name, as I explained before. For its part, the 6.7% of the classes have 3 names because they include 2 preferred synonyms in addition to the fully specified name, differentiating American and British English. So for example, the body structure third of esophagus, you can see it here. And with regards to the synonyms, we found that there are 0.53 synonyms per class, where the 65% do not have any synonym. This could be a point of improvement, I think. And well, for its part, the classes having synonyms present a median of 1 and a mean of 1.5 synonyms, but there are outlier classes with a high number of synonyms. So for example, the maximum number of synonyms is presented by the myeloid leukemia with 33 synonyms. Finally, there are 0.017 descriptions per class, where the 98% of the concepts don't have any description, which could be another point on improvement, in my opinion. For its part, the concepts with description usually have only 1. However, a few of them have 2, differentiating British and American English, as happened with the names. In connection with the object properties, the SNOMED CT has 120 of them. And here we found that each object property has exactly 2 names corresponding to the fully specified name and the preferred synonym. We also found that there are 0.058 synonyms per object property. Only the 5% of the object properties have synonyms, which could be another point of improvement. Regarding the descriptions, there are 0.375 per object property, where only the 35% of the object properties have a description. Here we found that some object properties, such as process duration, have 3 descriptions, also due to differences between British and American English. So we also studied these metrics by hierarchy. Here I show the number of synonyms per class because it was the metric with a higher variance among the hierarchies. And hierarchies like body structure, clinical finding, observable entity, organism, or procedure present a higher number of synonyms than others like environment, event, or biological product. This could be due to the nature of the concepts appearing in each hierarchy. For example, the organism hierarchy contains scientific names such as Canis lupus familiaris, in addition to the common name like domestic dog. This fact is specific for this hierarchy, which increases the number of synonyms, and this does not happen in other hierarchies like geographical location, for example. And we also calculated the global values of the metrics for the different versions of the SNOMED CT. We can see that almost all of them remain stable over time. This stability on the metrics could indicate that the SNOMED CT developers are following always the same strategy, that's having a well-cemented principles. And here the most varying one is the descriptions per object property, which was 0 until 2015. And from this year, the object properties began to be enriched with descriptions, as you can see in the yellow line of the figure. So now is the turn of the structural accuracy. We understand the structural accuracy of ontologies as the ability to appropriately represent semantics as understood by society. An ontology is a set of concepts related between them through relationships that can be hierarchical or not, and the structural accuracy refers to the degree in which these relationships are correct. So we can imagine an ontology as a building block game where each concept is a block. If the blocks are well connected, the structure of the ontology will be good, as shown in the figure on the top. Nonetheless, we know that ontologies can contain a huge amount of concepts, making it difficult to evaluate the structural accuracy. Besides, ontologies have to be adapted to the changes in the domain that they represent. For example, I'm sure that a lot of concepts related to COVID-19 have been included in many biomedical ontologies during the last year. Therefore, the life cycle of an ontology implies to remove and to include concepts. And since there could be many relationships between these concepts, the domain experts have to proceed carefully in order to prevent that a well-structured building blocks becomes something like this. Another important point is that it is difficult to automatically evaluate the structural accuracy of ontologies because you will need a domain expert. However, we can assist them with supporting tools. The idea that we propose is to compare the lexical content with the semantic content of ontologies. In other words, we will try to discover hints provided by the name of the concepts. And we will check if these hints are in line with the semantic definition of the concepts. So for example, here you can see a simplified hierarchy taken from this SNOMED CT, including the procedure and the qualifier value hierarchies. At first glance, we can see that cosmetic procedure is not in the procedure hierarchy, although its name could suggest that. On the other hand, all the children of procedure have the word procedure in their name, except in biopsy administration. These flaps could be due to a bad concept naming. So for example, biopsy administration could be renamed as biopsy administrative procedure, or a bad position in the hierarchy. So for example, cosmetic procedure could be a procedure instead of a qualifier value. Finally, a third option is that the lexical and the semantic content simply don't match, but this should be reviewed by a domain expert. Next, I will show our method to automatically identify and measure these aspects. First, I have to introduce three important concepts here. The first one is the lexical regularity. A lexical regularity in this context is a piece of text that appears recurrently in concept names. For example, here, procedure, administrative, or administrative procedure are lexical regularities because they appear in the name of several concepts. The second one is the lexical regularity class, or LR class. An LR class is a concept whose complete name is a lexical regularity. For instance, procedure and administrative procedure are LR classes in this example. And finally, we say that a class exhibiting a lexical regularity if its name contains a lexical regularity. For example, the concept cosmetic procedure is exhibiting the lexical regularity procedure here. These concepts are important because the structural accuracy metrics I'm going to present are focused on the lexical regularity classes mainly. So systematic naming is the first structural accuracy metric I'm going to introduce, and it checks if the name of an LR class is exhibited by its children. Let's see this with an example. In this hierarchy, there are two LR classes, as we have seen before, procedure and administrative procedure. So for each one, we check its subclasses. The LR class procedure has 3 children, and the lexical regularity procedure appears in 2 of them, considering positive cases. The concept biopsy administration would be considered as a negative case because it is not exhibiting the lexical regularity procedure. Thus, the LR class procedure has an individual score of 2 children exhibiting the procedure lexical regularity over 3 children in total. Similarly, the LR class administrative procedure has 2 children, but only one of them exhibit the lexical regularity administrative procedure. And finally, a global score for the ontology is calculated by dividing the total number of positive cases over all the cases in total. So in this example, we have 3 positive cases out of 5 cases in total, which results in a global score of 0.6. The other structural accuracy metric is named Lexically Suggest Logically Defined, or LSLD. And this metric complements the previous one by measuring the degree in which LR classes are semantically related with other classes exhibiting the corresponding lexical rurality. The hypothesis here is that the concept with a high level of similarity in their names should be related in the ontology. So let's see our running example to check how this metric works. Here we also focus on the LR classes. In this case, in the case of the LR class procedure, there are 3 concepts in the ontology exhibiting the lexical rarity procedure. 2 of them are subclasses of procedure, thus they are considered as positive cases because they are semantically related with the class procedure. Nonetheless, cosmetic procedure exhibits the lexical rarity procedure without having any semantic relationship with the LR class procedure, thus being considered as a negative case. Therefore, the LR class procedure has an LSLD score of 2 positive cases over 3 considered cases in total. Regarding the LR class administrative procedure, only one concept is exhibiting this lexical regularity, which is death administrative procedure. And this concept is a child of the LR class, thus being semantically related. Then this LR class would obtain an individual score of 1 positive case over 1 case in total. Here we also compute a global score for the entire ontology by dividing all the positive cases over all the considered cases in total. It's important to know that this metric is not only limited to the hierarchical relationships, but also another kind of relationships. So for example, the concepts left and pain in left arm are related through a laterality relationship that is also taken into account by the metric. So we applied these metrics to the SNOMED CT and we found 378 LR classes, including clinical concepts like hemoglobin or injection, general concepts like right or left, and another kind of concepts such as the preposition on or the verb thus. These LR classes are distributed along the SNOMED hierarchies, where the hierarchies with general concepts are likely to present a higher number of LR classes. For instance, the qualifier value hierarchy presents the highest number of LR classes, and this makes sense because this hierarchy contains concepts like this hierarchy contains concepts representing attribute values for defining other concepts. For example, the concept absent is appearing in concepts like absent plantar response or absent body position sense. Contrary-wise, the situation with explicit context hierarchy does not present any LR class. And if we inspect this hierarchy, we see that there are very concrete concepts like cervical cancer screening not done, and the names of these concepts are too long, which prevent that other SNOMED concepts could exhibit them. This could indicate that this hierarchy lacks of general concepts for classifying the lower ones. So these are the results of the structural accuracy metrics applied to the SNOMED CT, the version of 2019. The global score for the whole ontology are 0.171 for the systematic naming and 0.304 for the LSLD metric. In this case, the systematic naming, in the case of the systematic naming, the score distribution per lexical regularity class is quite higher than the global score with a mean of 0.64. And this could indicate that there are a small number of LR classes that have many children without exhibiting the lexical rarity of the parent class, thus provoking a low global score that is not reflected in the individual scores. In the case of the LSLD metric, the mean of the individual scores is 0.325, which is in line with the global metric. And next, I will show some individual examples. So this table shows the 5 LR classes with the highest and the lowest systematic naming values. For example, the concept diagnostic allergen extract has more than 3 children concepts that exhibit the lexical rarity diagnostic allergen extract in their names. And there are no children without exhibiting it, thus having a systematic name score of 1. Contrariwise, the concept oral dose form has 61 children that don't exhibit the lexical rarity oral dose form in their names, which provokes a systematic naming value of 0 for this class. Here we have the same for the LSLD metric. In the top concepts, we can see the concept oral dose form in the second position, with almost 3,000 classes exhibiting the lexical regularity oral dose form that are semantically related with the class oral dose form. On the other hand, if we inspect the concepts with the lowest value for the LSLD metric, we found very general concepts like containing, entire, or in, and these are common words that are likely to appear in the name of the concepts. So for example, entire Bartholin's gland or in full remission. But these kind of concepts are not being used in the semantic definition of those exhibiting their names. Oral dose form is a remarkable example because, as we saw in the previous slides, this LR class has a value of 0 for the systematic naming metric. However, it has the maximum value for the LSLD metric. This means that the children of the concept don't exhibit the lexical rarity oral dose form, but this lexical rarity is exhibited by other concepts in other points of the hierarchy, and these other concepts are semantically defined by using the concept oral dose form. Here on the right, there are several examples of concepts that contain the lexical rarity oral dose form in their names and are related to the class oral dose form through the relationship has manufactured dose form. So these are the distribution of the individual score per lexical rarity class grouped by hierarchy. If we inspect, for example, the qualifier value or the SNOMED CT model component hierarchies, which were the ones with the highest number of LR classes detected, we find that in general, LR classes have a low value for the LSLD metric and a high value for the systematic naming metric. This means that the children of the LR classes usually exhibit the name of the parent class, but this name is also exhibited by other non-semantically related concepts. Other important hierarchies like body structure, clinical finding, or procedure present values with a median higher than 0.5 for both structural accuracy metrics, which indicates a substantial agreement between the lexical and the semantic content. Here we see the evolution of the global values for the structural accuracy metrics from 2011 until 2019. The metrics present stable values under 0.3 in time. And as I said before about the readability metrics, this stability indicates a mature ontology in which the same design principles are applied in different releases. Moreover, I think it's important to remark again that the low values for the global metrics are due to high number of negative cases for some LR classes, which provokes a drastically drop in the global values. So finally, here I have collected some conclusion or take-home messages that I've learned during my research. So high values of readability facilitate the use of the ontology, as I shown with some examples. High values of structural accuracy indicate a well-structured and semantically related content. And the metrics presented here show potential point of improvement. So for example, in connection with the readability, I think the lack of descriptions is the most critical, but there are also many entities without synonym. I think this is a point of improvement. And with regards with the structural accuracy, some concepts follow a systematic naming, but other not. And the name of some concepts could suggest semantic relationship with other concepts that are not included in the semantic definitions. So I think these things, it would be interesting to focus a little bit on it. So now I would like to say thanks to all people that collaborate with us, and also to the Spanish government and the European Union for funding this research. And of course, thank you so much for your attention. And here you can see some links that you can check if you are interested in. So thanks so much. And I think we have time for questions.
Yes, we do. Thank you so much, both Professor Fernandez and to Francisco. I read this article about a year ago, and huge fan, and this presentation just kind of filled in some of those connections for me. So thank you. This was for my own edification as well as for the SNOMED CT community. So thank you.
Thanks.
Attendees, go ahead and place your questions in the Q&A chat box. I do see a couple of questions in there. So let me get to those. Okay, so John says or asks, can these quality metrics be applied to a specific module ID in SNOMED so that it could run a specific extension, such as the US extension, and a comparison be made between the extension and the international core module? Great question.
Yes, you can apply the metrics to any ontology expressed in OWL. So you can take the version of SNOMED that you want, translate it into OWL, and compute the metrics. Yes, you can do that.
And I did see your GitHub URL on that last page. So
yes.
Yes, and I would like to add that in some of the studies that we have mentioned in the presentation, we have actually applied the metrics to modules of SNOMED CT. I guess here this John Snyder is referring to international extensions, right? Or to specific extension of the SNOMED CT. And we, in previous research, we have extracted modules from SNOMED CT in order to run specific tests. So, I mean, as Francisco has said, as long as we are able to express or to represent in all the module we want to analyze, we can apply the metrics. And we can compare between the different modules, the results, and not only at the level of metric, but the metric is the result of some kind of mathematical calculation, but we've got the results of the metrics for every concept or for every LR class. So we can make comparison not only at the level of metric, but at the level of particular classes or particular regularities.
Looks like John had a follow-up. If analyzing the core module to an extension, what kind of metrics could you put in place to specifically look at the offhand from the international module to the extension module concept?
I'm trying to understand the question.
Yeah, John
yes.
is raising his hand. So John, I'm going to allow you to speak if you are connected. Let's see.
Thanks, Susie.
Yeah.
So basically, if you view the line between the international edition module and an extension module, it's kind of like tearing a sheet of paper and you end up with a ragged edge. So what specific measures could you put into place from a quality perspective to look at those concepts that are on that ragged edge that basically pass off or hand off from the international edition to the extension?
That's a good question, because I mean, one thing that could be done, I mean, we've got metrics whose objective is to measure and to describe a particular module or the particular ontology. And here, what you are trying to do is to do something slightly different. Is to, okay, I've got this international module, I've got this extension module, and if I am interpreting right the question, you would like to make, okay, which of these modules, which is the handoff for using the international module or for using the extension module? Which kind of benefits I can get if I use one or the other? Is that right?
No, it's if you look at it, that ragged edge from a hierarchical perspective, you have a parent concept in the international edition and you have a child concept in the extension. And what quality measures would you specifically look at to compare those two and all the concepts that exist on that ragged edge between the...
Okay, you mean that, okay, if you don't use this extension against using the having only the international module and having the international plus the extension.
Right. That dividing line between the two, you're going to have some concepts in the international module, and that child concept will be in the extension module. What quality can you specifically look at in that handoff situation across the entire, all the concepts that exist on that ragged edge?
And actually, you could perform an analysis only on the international modules, an analysis on the international module plus the extension module, and then look for the differences, and also to analyze the quality of those concepts which are only in the extension module to see or to whether they are contributing positively or negatively to these metrics. But actually, I think it would be interesting to maybe based on the existing metrics to define a specific metric which is based on this one, which take into account all these aspects related to this, let's say, this connection between the international module and the extension, because it's something very specific which can be addressed by using the metrics. But for example, this one that we have defined, if someone is interested on this structural accuracy, or the other metrics that we have defined and we're applying from the quality assurance perspective of the ontologies. But since the analysis has a concrete goal, which is, okay, I've got this international module, I've got the extension, what is the impact of this extension to the whole quality, or what's the quality of only the extension? Some particular metrics related to the impact of this extension could be defined. But actually, we could use more or less the same metrics than for the ontology, but just analyzing them or interpreting them or giving the values, taking into account that only some concepts are new and they have been defined in a different module. But at the end of the day, if you look at the international module plus the extension module, it's like you have a new module in SNOMED CT. You have different hierarchies. You have the different hierarchies can also be considered like different modules in SNOMED CT. And I think more or less the metrics can be applied, but in order to simplify the interpretation, maybe some additional metric could be customized for this situation.
Great, thank you.
Sorry. Am I presenting the thank you screen here, hopefully? Okay, and let me check if there are any further questions. Not seeing any. Let me see if there are any other hands raised. Not seeing any. Okay, great. Well, thank you. Thank you, everyone, for attending today. So my email is up on the screen. Let me also share my video here. Sorry. I got a new monitor and I'm all discombobulated. Anyway, so thank you for attending today. If you have any further questions for Professor Fernandez or for Francisco, please email me. My email is listed up on the screen, and I will get your questions over to them. The slides from today and the video will be made available later this week or next week. I will email all those registered, so you'll have links to that. Other than that, next month we have the SNOMED CT Expo, so hope to see you guys there. And we will reconvene for the SNOMED research webinar in November. So until then, thank you. Be safe, stay healthy, and I will see you all then. Thank you. Bye-bye.
Thank you. Bye-bye.
Bye, thanks.